Okay, so welcome everyone. So today we will be again doing PN acquisition, PN sequence acquisition that we have been doing in the previous class. So today's week will again be mostly theoretical instead of problem, because in this week also you have the MATLAB code based problem. So there is not much problem to solve in this week's material. So this will mostly be a theoretical recap of the problem solving session of the sessions that have been conducted in this week by Professor Devarati sir. So I will be doing a brief theoretical recap of that, and after I have done that, I will entertain your questions, and that will be all. In the next week, we hope to start problems again based on the topic that will be taught in the week 8. So today's will be mostly theoretical and based on the presentation from which you are being taught. So I will be mostly doing a theoretical recap of that. So we have done PN acquisition. PN sequence acquisition is the method of regenerating the PN sequence that has been used at the transmitter at the receiver. So there has been a PN sequence that has been used at the transmitter. Now your aim is to regenerate it at the receiver so that you can despread the spread spectrum signal and retrieve the message. So the other methods have been used like correlation. Today we will be using matched filter. So correlation technique has been covered in the previous week, but the active correlation in the signal in the for a BN sequence is computationally harmful, because a multi active correlation means you are multiplying the signal and the delayed version of the signal and then adding them or integrating them. So a multiply and integrator type of correlation detector structure is typified by the fact that the local PN generator. So there is a constant local PN generation that is happening, and you are correlating with that with the received signal to see what signal you are getting, and based on the feedback you are adjusting the PN sequence. So hence a completely new set of n equal to tau d by tc chips of the received signal is used for each test. So this test is basically the feedback in which you decide whether you are arriving at the correct PN sequence or not. So now based on that also there have been multiple methods, like in the single dual correlator, where you only get one single window to determine the PN sequence, and then you have to carry on with the despreading operation. And then there are multiple dual signals where you have to, of course, eh, so where you have to use multiple duals, that is multiple slots, to modify the PN sequence as the as and when the situation changes. So, wait a minute. Sorry for the network interruption. So, so the hence a completely new set of chips of the received signal is used for each set. This poses a basic limitation on the search speed since the local PN reference phase can be updated only at tau d second intervals. So the local PN sequence can only be updated on the tau t second interval. Thus, if search is conducted in 1 by n chip increments, the search rate of a single dwell search technique is 1 by n chip positions per second. The search rate, the search 1 by 1 by tau t into 1 by n minus chip positions per second, 1 by n chip positions per second. So the search rate of a DS acquisition scheme can be significantly increased. So basically, at every 1 by n chip increment, at every tau d by tc time, it is generating a new set of PN sequence. That is the crux of this point. So because it is generating a new PN sequence each time, so the search rate is getting slow because the generation of PN sequence takes time. But the search rate of a DS acquisition scheme, that is direct sequence space spectrum acquisition scheme, can be significantly increased by replacing the multiply and integrate operation with a passive correlator device such as matched filter. Okay, so there are multiple ways of implementing a matched filter like charged couple devices, surface acoustic wave convolvers, discrete time correlators. So in the continuous time case, the received PN waveform plus noise is converted with a fixed finite segment of the PN waveform corresponding to say n chips, and the continuous output is tested against the threshold to determine when acquisition has occurred. So instead of generating new chips every time, what you are doing is you are keeping a small window. So here the difference is that you are keeping a so here the difference is that you are keeping a small window of PN sequence that is being matched. So instead of matching the entire PN sequence, you are matching small windows. So your PN sequence updation. So one sequence, if you say divide it into four windows, then one sequence will last four times the amount of time it would have lasted if you have matched one sequence entirely in one go. So if you match the local sequence with the spread sequence in one go, of course you have to again regenerate. Then you have to again regenerate. But here, if you are only you are dividing it into windows, so you have to only take into account the windows. So take into account the window to window matching. So in that window to window matching, if there is a threshold accuracy threshold being crossed, you can say that acquisition has occurred. So if a single sequencer is divided into four windows, then it will take it will take for it will take means it will last for four times the amount of time that would have lasted if it was compared in one go. So in this configuration, the input continuously slides past the stationary stored PN waveform replica until the two are in synchronism, at which the threshold would be exited and the local PN generator input. So instead of the entire thing, you are keeping a window and you are continuously sliding past that window. That window is basically continuously sliding. So the continuously being slided. So we will the input continuously will slide the window of the input will continuously slide against the window of the generated PN sequence replica, and if that window only matches, we can say that the entire thing has matched, and we will go along with that. Now, in direct sequence space spectrum system, the PN spreading waveform is typically biphase modulated. Biphase means plus 1 minus 1, modulated on a carrier whose phase is yet unknown, is as yet unknown at the receiver. So the amplitude is known, that is 1, but whether it is plus or minus, that is not known at the receiver. The matched filter acquisition system must be implemented either in a band pass or an equivalent low pass version. So the first one is the band pass version of the matched filter. So here you have the received signal, you pass it through a matched filter, and then you basically extract the envelope and compare the threshold to get the decision whether the code has been acquired or not. So when the matched filter will completely match the received signal, then only the square envelope will give a higher threshold, give something higher than the threshold. So you will say a matching has occurred. You can also do it in low pass equivalent version, where you will basically have two band passes, one in the I and one in the Q, and then you will add them to get the equivalent low pass. Okay, in the former case, a bandpass match filter is used whose maximum output is detected by a square law envelope detector. In the latter phase, the in-phase and quadrature carriers with arbitrary phase but unknown or estimated frequencies used to demodulate the received signal, followed by a baseband matching filtering of each demodulated signal. So here you will need a carrier, of course. Here you will not need a carrier. Consequently, the implementation of a matched filter for a finite length PN waveform is most easily visualized in form of a yeah. Okay, conceptually, the implementation of a matched filter for a finite length PN waveform is most easily visualized in the form of a tapped delay line, followed by passive filter matched to a single PN chip waveform. So, uh, this is another way of thinking about the PN sequence, the some PN sequence acquisition mechanism, that you are basically delaying and adding, delay and add, delay and add, and then you are getting a particular sequence, tap delay line implementation, and then you are finally passing it through a matched filter to get the PN sequence. So this figure 2 can be shown to be equivalent of figure 1. So figure 2 is a conceptual implementation of what is actually done in figure 1. Now, a match filter is generically a passive device that maximizes the signal to noise ratio at its output when the signal at its input is embedded in additive white Gaussian noise. So, if there is signal plus noise, so if a signal is coming and there is a AWGN, ideally the passive filter, matched filter, will be the filter at which filter coefficients at which you will get the maximum SNR. So, the impulse response of this matched filter is given by the reverse of st in t0 seconds time slot, that is ht equal to s t0. So, whichever signal is there, the t0 minus t version of that. So, flipped and delayed version will be known as the matched filter of that signal. So, each signal or each PN sequence chip or PN code has a matched filter. So it's not like there is a unique matched filter for everyone. So every PN sequence. So for every PN sequence chip, you have to either dynamically change the design of the matched filter, or you have to use a different matched filter. So of course, different matched filter is not possible when you have lots of ports. So what you do is you take something like this tap delay and you adjust the coefficients accordingly. Now, So this is the frequency domain transformation of the filter. You can just follow this derivation. Next. Hmm. So the discrete time version, now you will go to a discrete time version. Uh, yeah, the discrete time version of the matched acquisition system. So the previous match filter acquisition system was a continuous system. Now if you want to discretize that system, the steps are that basically you have to modify this integration. So this xt is equal to st. So for xt is equal to st, then it will this S is basically the PN sequence chip that is like that is based on the match filter. Like you have designed the match filter for a corresponding for a PN sequence chip. So that PN sequence chip is ST, and of course when your this signal will match the matched filter it has been designed for. So the matched filter it has been designed for is ST. So the the match filter it has been designed for is ST. So the signal XT that is incoming, it will give the maximum SNR or the square law envelope detection mechanism. Square law envelope you can see here. This is the square law envelope. So this square law envelope will be maximum when of course your XT will match ST. That is the sequence you have designed for. If your incoming signal matches that, you will of course have the maximum value. For any other xt, of course you will have now some different value which is not simply s squared t but something less than s squared t, integration s squared t. Now if we sample this output at time instances n plus k by n, that is at at a multiple of n of the chip rate, at a multiple, so the at every multiple of chip rate, so 1 by n is the chip rate. So at every multiple of chip rate if you sample, then the corresponding value you will get is something like this, where dn is plus 1 or minus 1, that is the amplitude of the signal. So dn is plus 1 or minus 1. Finally you will get the sample to be di into xi plus k, where k is the multiple of the chip rate that the current sample is in. So this is a form of discrete time correlation. This can be implemented. This can be easily implemented because di is plus 1 minus 1 and xi plus k is the basically the delayed version of the incoming signal. It can be implemented in analog or digital form using tap delay or shift register. In the latter case, the contents of the shift register which holds the signal sample digitized, and the holding register which permanently contains the fixed segment of the code. So if there is a shift register, there will be a one in which the signal samples will be stored and in another in which the data will be stored. Now they will be correlated, and of course the if they match, then the threshold will be, the value will be maximum, it will cross the threshold, you will say PN sequence acquisition is complete. So this is the diagram for this PN match filter rapid acquisition technique. So the since for either analog or digital configuration, the outputs occur and are ultimately threshold tested at n times the chip rate. The search rate is for this acquisition is n by tc. So the previous integrate and add correlation that we have used, that had a search rate of, where was the search rate? So it had a search rate of 1 by tau d. So now you, instead of uh, 1 by tau d, what you have is n. So you are doing n times faster, so n by tc. Okay, so here n by tc, n by tc can be shown to be much greater than 1 by tau d, because it is n times more. There is a n here, and this n can be pretty large. So this value is, the search rate is much higher. So tau d by tc is basically n. So it is higher by n by n. N into n. It is n into m times faster than that of the serial search technique. This large apparent improvement in search rate, or equivalently the time to search over the total uncertainty region, is a consequence of the fact that in MF system only one new fractional chip of received signal is used for each correlation test. So here you are only correlating small blocks at a time. You are not correlating the entire thing at once and then again entire thing. So you can reuse the code. You can reuse the code for a longer time, and also you are making decisions much faster as compared to, yeah, you are making decisions much faster as compared to serial correlation. Now, হ্যাঁ বল, হ্যাঁ বল, ক্লাস নিচ্ছি, ঠিক আছে। Yeah. So the large apparent improvement in search rate, or equivalently the time to search over the total uncertainty region, is a consequence of the fact that in the MF system only one new fractional chip of received signal is used for each correlation test. Because of this fact, however, it would appear that the noise corrupted correlation value from the test to test would be highly, because of this factor, however, so now it is, since it is testing each time over a small parts, so of course it is, and making decisions, so the rate of decision is much higher. But because of this fact, however, it would appear that the noise corrupted correlation values from test to test would be highly correlated because of the nm-1 sample overlap, as contrasted to the same test values in the single dwell serial search method. Okay, so if there is a noise, a corruption, because you are taking only one bit at a time, so you have very little data to weed out the noise. So your noise will pretty heavily, if that noise is corrupting that bit, so your noise will be pretty heavily, this influenced by the no, sorry, the detection process will be pretty heavily influenced by the noise. So in other words, this noise, this is not as robust to noise as serial search. So serial search may be more expensive, but it is more robust to noise. So now there will be, let us now present a method of verification of the threshold crossing event for the system. So now we want to verify whether we have, like, we want to discuss the method to verify whether we have crossed the threshold or not. So we have crossed the threshold. If we have crossed the threshold of accuracy, we will say that the PN sequence detection is, acquisition is done. Okay. So now, in particular, non-coherent correlator structure that is shown here. So you are not requiring any local carrier. You are just correlating and making decisions. So it is a non-coherent detection. It is followed by a coincidence detector whose operation is as follows. Upon a tentative decision of an in-sync condition, the local PN segment used for code weighting in figure 1 or store figure 1 means the this one. Yeah. So an analog correlator with match filter implementation is figure 1 here. So upon a tentative decision of an in-sync condition, so your threshold has been crossed and you say that PN has been acquired, your PN sequence is in sync with the actual sent PN sequence. Upon a tentative decision of that, corresponding to hypothesis H1, the local PN segment used for code weighting in figure 1 or stored in the holding register of figure 2 is now updated by the local PN generator. Hence, for a specified, so basically your PN sequence, PN generator now starts using that particular PN sequence. Hence, for a specified interval of time, the input code and local code segment remain at a fixed relative time offset. During this time interval, the non-coherent detector continues to make threshold tests. However, to strengthen the reliability of the verification operation performed by the CD, these tests are now conducted over disjoint MTC seconds interval of the received waveform and are thus statistically independent. In so basically, the threshold tests, instead of continuously doing that, because continuously doing that, what will happen? You have made a decision for an in-sync and you are relaying that to the PN sequence generator, but in that particular time also it might be making a decision and that decision might be erroneous because the in-sync decision has not yet arrived and the PN sequence has not yet been updated. So in that particular type, of course, there might be a chance that you will commit an error. So, however, to strengthen the reliability of this verification process performed by coincidence detector, these tests are now conducted over disjoint MTC second time interval. So, basically, instead of continuously doing that, you do it in blocks of time. So, you first do it, then you wait, then you do it again, then you wait, like that. Okay, so this is the at MTC, at every MTC time. So 0 to MTC, then you take some gap, then you do another MTC interval, like that. If A of these tests are performed at the time interval TP, that is TP equal to AMTC, then the rule used by the CD for a final acceptance of H1 hypothesis. H1 hypothesis means PN sequences are in sync. So is that B out of A of these correspond to threshold crossings. So B is a particular number. So B can be say half plus 1. So if 100 tests are performed, at least 51 of them should correspond to threshold crossing. So instead of making threshold crossing decisions while also changing the code, you will first change the code, then you will do threshold crossing decisions. Once you have done A threshold crossing A tests, and out of those, say B is less than A, so B may be half of A or 70% of A or something like that. Because of this, when you have done B out of this successful threshold crossing, you will say that your PN sequences are in sync. So you are not making the decision instantly, but you are waiting for A decisions. You are waiting for B decisions out of total A tests to be in your favor. During this during this time interval, the non-coherent continue. Okay. So upon successful completion of this majority logic decision, the tracking loop is activated. Whereas upon unsuccessful completion, that is fewer than B out of A threshold crossings, the local code segment again is held fixed and the search continues. So this is how you make a decision whether your PN sequence acquisition is complete or not. The acquisition of fast frequency, now we have done DS3. PN sequence acquisition for DS3. Now we will do PN sequence acquisition for frequency hopping. So now we will do for frequency hopping and MFSK. So the acquisition of fast frequency hop signals and slow frequency hop signal will be considered. So fast frequency, there is a fast frequency hop signal and there is a slow frequency hop signal where the rate of hop, how it depends whether it is fast or slow, you basically decide on the rate of hop. So if you are changing frequencies within a chip, so your entire core sequence, if within the sequence only you are changing the frequencies, you are fast doing fast frequency hopping. However, if your chip rate is higher, that is your chips are changing 2, 3, 4 times, then your frequency is hopping, then you are doing a slow frequency hopping. So it depends on whether the chip rate is greater or the PN sequence, the hop rate is greater. So if the hop rate is greater, it is fast. If the chip rate is greater, it is slow. So the acquisition of fast frequency hop signal and slow frequency hop signal will be considered. MFSK modulation changes the carrier frequency to one of M tones so that there are M possible frequencies around the carrier frequency. So MFSK is multiple frequency shift keying you are doing. So MRE frequency shift keying basically. So in MRE frequency shift keying you have M equal to say 4, 8, 16 like that tones. So there are say 16 or 8 possible tones around the carrier frequency. For fast frequency hopping, the MRE frequency is the same over the hop duration. For slow frequency hopping, it will be assumed that there will be one MFSK tone over the entire hop duration. So because it is slow frequency hopping, so the frequency won't change because it is not hopping. So there will be only one tone. So in the fast frequency hopping, it is the tones are changing. So sorry, the tones are changing. Yeah, the same tones are changing because it is making hops. So that is what is written here. Now figure okay. So see, this is the particular search acquisition active serial active search for acquisition of FFH, that is frequency hopping, MREFSK signal. So basically you pass it through a demodulation, use accumulate, and then you select the maximum, and then you compare with the threshold, and if it is yes then good, if it is not then you continue PN generation. So you may generate the next PM and check. So basically you are continuously checking the various PN sequences to the one that is actually incoming till you get a match. So yeah, each MFSK frequency, so what is the mechanism here? Each MFSK frequency is correlated over n hops and the maximum is selected. So basically your MFSK is correlated with, because MFSK means there can be m tones. So and there can be n possible hops. So it first we have to choose which hop. So each MFSK frequency is correlated over n hops. So all the at all the n hops you run a correlation, and the one which actually is the one which actually matches will of course give the maximum correlation value. Okay, if more SNR is needed for acquisition, then multiple MFSK sequences symbols can be accumulated together in a sequence. Since it is assumed that there are n frequency hops per MFSK tone, the modulation for fast frequency hopping, then a symbol period has a duration nth. So there are n hops in one tone. So the tone duration will be of course n into the hop duration. For fast frequency hopping, each MFSK symbol frequency is the same over each frequency hop. So each MFSK symbol frequency is same. So we are assuming one thing, that within a particular hop, so when it is in a particular hop, eh, in that small duration, the tone of the MFSK is not changing, because that will make our lives very difficult. So if the hop is fixed, we will assume that the tone is also fixed. So if the hop is fixed and the tone is fixed in FF spread spectrum, then of course the total frequency is fixed. We have to assume that the total frequency is fixed. So how to assume the total? How to ensure the total frequency is fixed? We ensure that during a particular hop, the tone is not changing, or in case of slow frequency hopping, we assume that in the particular tone the hop is not changing. So a tone and a hop together will make the frequency constant if they both are held constant in a particular duration. Since it is okay for fast frequency hopping, each MFSK symbol for okay. So now this is a timing diagram for the PN sequence acquisition. So there is FSK, FSP, FSQ. These are the tones of MFSK, and then each tone is, because it is fast frequency hopping, each tone is hopping across multiple frequencies. So F1, F2, F3, F4, then F5, F6, F7, F8, like that. So when you receive it, what will you get? You will get F1 plus FSK plus delta F, where delta F is like the frequency deviation. So this is, you can ignore for now. So basically the hop plus the NFSK, because it is constant throughout. So your received frequency is determined by two things. One is the hop sequence frequency and one is the NFSK sequence, NFSK frequency. Now you do a receive frequency synthesizing, and using a mixer you will create the signal present sequence. Now this signal, this mixer will basically mix your signal with a local tone to get the signal. So this timing assumption and relation of frequency hops for FFH, MFSK and the NFSK symbols are illustrated. It is assumed that when the receiver dehopping synthesizer is offset by epsilon second from the received hopping waveform. Okay, so of course there will be a delay between the transmission process and the received process. So it is assumed that when the receiver dehopper is offset by epsilon, so there will be an offset by epsilon here, of course, because that is the time that is taken from the transmitter process to start and the receiver process to start. So okay. Mm, the top row illustrates, in figure 2 illustrates the timing and frequency diagram for FFH MFSK signal acquisition system. Yeah, so now this is the timing and frequency diagram, like I said. So here you basically get the hop and you get the MFSK, you combine them, and basically you get the received sequence. Now this received sequence will be passed through a local mixer. It will multiply, that is, it will mix with the local oscillator frequency generated, and based on that product, it will make a decision whether signal is present or not. Okay, we will now be doing an analysis of the code acquisition. So we'll be doing an analysis. We will first take a small break, and maybe what 5 minutes. We'll take a 5 minutes break. Then we will go into the analysis. Okay, so yeah, let's go into the analysis of the frequency hopping signal PN acquisition. So we assume a transmitted signal like this. This is basically the hopping spread spectrum. The omega is giving the tau MFSK modulation tone, and omega I is giving the hopping frequency, and TH is the fast frequency hopping duration. So it is a pulse of the duration with multiples of TH, where TH is the hopping duration and PT is the signal power. So it is lasting for TH duration and it has two frequencies together added. One is the frequency hopping frequency and another is the frequency shift keying frequency. The phase I is a phase value for the ith transmitted frequency hop signal and is expressed in radians. So the received signal, assuming that it is only a modified, okay, the phase is a phase value for the ith transmitted frequency. The pulse function is defined as pt equal to 1 or 0. So these are the constant things. Theta is phase and p is the pulse function. So the pulse function is designed such that it is one within the hopping duration, because this omega ith hopping frequency will only last for the ith hopping duration. It will not last beyond that. So as the hopping frequency changes, the particular pulse has to be turned down. Okay, the received signal, now this signal is the transmitted one. Okay, this signal is the transmitted one. So the received signal is the same thing, but which is modified by Doppler. So it has a noise. This is the noise. This is noise, and the in divided into the quadrature and in phase components. And this is the frequency, and it is only divided, only getting a frequency shift delta f, that is written here. So that is the Doppler shift. So it is only getting the Doppler shift, nothing else. So the dehopping signal will be something like pt minus kth cos omega k minus omega if. So here again we are multiplying with the omega if, which is the local oscillator type frequency. So intermediate frequency it is called. So it is like a local oscillator type frequency. So we are dehopping using that. So this is LO, local oscillator, and this local oscillator frequency. So this local omega if is the local oscillator frequency, and t is the pulse. Again it has to be one within the hopping duration, and it is subtracted by epsilon because there is a lag between the transmission process and the receiver process, that is the propagation lag. So because of that there is a epsilon delay. Okay, so now you combine them. So the difference frequency term out of the mixer is given as, so yeah, you combine them and you first minus theta. So yeah, you multiply this. So what you do is, because this is a mixer, so the dehopping signal has to be multiplied with the transmitted signal, and you will get something like this. It will have the pulse in the square form, and it will have a cos component and some residual terms, which is denoted by O2 omega 2 omega 1. And then there is another pulse which is in the pulse which is multiplied by the noise. So the noise is also getting shaped by the transmitter pulse. So this is the non-coherent demodulation. Now if you simplify that, The in-phase and quadrature components can be neatly written like this. So it is the product of two pulses. One is pt minus kth, another is pt minus kth minus epsilon. Since epsilon is very small, you can say it is like a square of a pulse. And then there is the cos component plus in-phase noise, and then there is the sine component minus quadrature noise. So this is the in-phase and quadrature parts of the signal. So I is denoted as is plus in, and q is denoted as qs plus qn. So n is the noise component and s is the signal component. So the in is basically this and the qn is this. So these are the noise parts. So is square plus qs square, if you do, you will get some value like this. And the correlation, okay, so in and qn. Now if you, it follows that the output of the signal component out of demodulator is given by the sum of square. So output of the signal component out of the demodulator. So since the demodulator now has a square law detector, so here you will see there is a square law detector. So whatever I you are getting and whatever q you are getting, so you will do I square plus q square. The noise and the signal both will have I square plus q square. The noise I square plus q square you can do like this, and the signal also you have to do I square plus q square. So the signal I square plus q square is given like this. It's like a sine x square by x square kind of thing. So it is a complicated signal. It is a sync into x square kind of thing. Then the correlation of the frequency hopping signal for a frequency error delta f and the time error of epsilon second is the same as root is square plus qs square when p equal to 1 and fsj equal to fsl. So what is fsj and fsl? Fsj and fsl are two frequencies. Okay, so when the two hop, basically kind of autocorrelation when you do, and p is equal to 1, you will get the correlation of the fh signal. So this, it is shown that this root under is square plus qs square can be shown to be the correlation. Now okay, now we will do some probability analysis of this frequency hopping and active search thing. So the probability density, yeah. So first consider the variable y. So now we have to do a probability analysis. We have initialize a variable y, which is the ith hop square of the in-phase and quadrature parts. Then the probability density of y is given by this gamma distribution. Why? Because it is in the square form. So it is given by the gamma distribution, and yeah. So now you do a variable change and you will get this kind of a probability distribution. Yeah. The now consider the case when the signal is present. The probability density function of the signal is given by py equal to Okay, first you take signal is absent. Sorry, yeah, that is what was missing. So first we consider the case when signal is absent, signal is not present. Then your in phase and quadrature are nothing but noises. So in phase square plus quadrature square will be Gauss square plus Gauss square. So you will get something like a gamma distribution. Now, if you take a variable transformation, you will get something like this. So this is your pure noise. Now when the signal is present, again you will get a gamma distribution, but this gamma distribution will be scaled by the signal S. So you will get something like this. Okay. So where S square is, why it is scaled by S? Because the signal, the randomness is coming from the noise only. So the noise was pure Gaussian once, but now it is Gaussian, which is now it is Gaussian, which is this. Yeah, now it is Gaussian, which is scaled by the signal. So because the Gaussians are scaled by the signal, so if you take a square, you will get something like this. Okay. Now these probability distribution derivations are not included here, so you don't have to bother with that. So finally, you get something like this, where when there is signal plus noise, it is e to the power gamma and e to the power z. So when the timing is more than one hop in error, the signal is absent and a false alarm occurs when one of the n noise only correlator output exceeds the threshold. So if a noise only correlator output, that is like this kind of an output, it exceeds the threshold, you can okay. So when L was added, so now you have to derive the false alarm probability. False alarm probability means the signal threshold with only noise, your threshold will get crossed. So yeah, let Zi be the probability of not having a false alarm is given by that all the variables will be less than the threshold. So it is that this particular distribution, all of them will be less than the threshold. So you get something like this. So 1 minus 1 minus. So because all of the variables are independent, so 1 minus e to the power minus this thing, exponential distribution, and these are multiplied to the power n m. So and PFA is the 1 minus of that thing, that all of them are less than threshold. So if one of them is greater than threshold, you will get an alarm. So it can be shown that the false alarm probability is basically e to the power minus eta, this thing, summation nc minus 1 eta to the power k by k factorial. So the probability of detection occurs when the probability of detection occurs when the correlator with signal exceeds the threshold. So now first was false alarm, but what if signal itself was present? So now you have to do the threshold crossing such that one of them has crossed the threshold and the others have not. So Z1 is greater than eta and others all are less. So this one again, you do a noise distribution of this density function, and this you do a distribution addition, so you integrate these distributions, and these are the distribution, the detection probability is something like this. So it is very difficult to evaluate, so you don't have to dwell much time on it. So now, which is something that is actually solvable, is the mean and variance of the acquisition time. The mean time is given by this expression, that is depending on the probability of detection and the probability of false alarm. So usually we decide a particular probability of false alarm, and then we decide do a probability of detection around it. So this is the mean time to acquire a single active correlator. And now the mean is given by this. So we design around a particular false alarm, and then we derive the detection probability for that false alarm probability. And the q is the number of code phases that has to be searched. So this is the mean time to acquire, and the variance is basically this tau d dash is nth or nts. So if it is slow hopping, it will be the symbol rate or the chip rate, and if it is fast hopping, it will be given by the hop rate. So that tau d dash. Now the variance is basically tau d dash square, and it will depend on the PD, and 1 by 12 minus 1 by PD plus 1 by PD square. The derivations of these expressions are very difficult, so you have to just by heart the mean and variance, because that might be important. The particular probability of detection value is, of course, this is very hard to solve in your actual exam. So you have to by heart the mean and variance. That will be important for your problems. So consider an example of acquisition for slow frequency looping. So we have a numerical example now. Assume that the time is unknown, 2000 symbols, and 8 FSK modulation is used. So 8 FSK modulation means is used. So MRE is M is 8. Let K equal to 3 and assume that PFA is equal to 10 to the power minus 4, 5, 6, 7, basically varying. Also let gamma equal to 1. What is gamma? Gamma is basically the threshold that has been, yeah, gamma is this. Gamma is basically a signal threshold that has been defined. Okay, so that is gamma. Determine the mean acquisition time in this case as a function of the n, the number of modulation symbols that are combined per hop. Okay, so here we have to plug in the values of the mean acquisition time. So here you have 2 plus 2 minus PD into q minus 1. So here this q you will leave, q you will, how many codes have to be searched? Okay, 1 minute. So PFA you will put 10 to the power minus 4. Q you will go put 1000, because 1000 is there. Code phases you have to search. No, code phases, not symbol. Sorry, Q will not be 1000. So you will put PFA and K from here. So PFA is 10, say 10 to the power minus 4, K is 3. And then you give the tau d dash. What is tau d dash? Tau d dash is here NTS. So symbol, because it is slow frequency hopping, so it is N into TS. So what is N? N is the number of symbols, that is 1000, and TS. TS is your symbol rate. So yeah, so TS is your symbol rate. TS is not known, so you will leave it as like that, TS. And then PD you have to derive from here. So yeah, PD you have to derive from here. Now the problem is deriving PD from here is not possible mathematically. Okay, so you need the help of a computer. you have to feed the particular integration solution for to the computer, and it will numerically solve the integration to get the PD. Once you know the PD, you can plug in all the values here and you can get the particular this n value. So say the n, there are 1,000 symbols. So if 1,000 symbols, say they are transmitted in 1 second, okay, so your NTS, so your TS is 1 by 1,000, but your n is the number of symbols you are combining, that is unknown. So it can be 100, you can be 200, it can be 300. So if it is 100, then tau d dash will be 0.1. If it is 200, tau d dash will be 0.2, like that. Okay, so you will have the value of tau d dash. And yeah, Q. Now Q, how many phases you have to search? Code phases is basically you have to search because there are how many possible codes are there. So if 8 FSK is there, so 8 FSK means you have to search through 8 symbols. So you can put Q as 8 here. Basically it is the number of symbols you have to search through. So you have to, for demodulating, so you have to first put 8 here, and PD you will get the detection probability from here. So that you have to use the numerical analysis for, and finally you will get a result like this. Okay, so yeah, now we will be going over the MATLAB code generation. For that will be your assignment for BER generation or spread spectrum. So you have done QPSK, but over non-spread spectrum, that is over narrowband channel. But now they will say to, now they will say to give spread spectrum BPSK over AWG. So you have to write a MATLAB code to generate spread spectrum in BPSK, and you have to give the SNR analysis, so BER versus SNR. So how will you do that? So you will of course generate 3 to the number of symbols, and now you will have a code matrix, that is the 4 length Hadamard code. Okay, so 4 length has 3 volts for Hadamard code, 4 length you generate, and then you generate the bipolar sequence for transmission, and then basically you spread, you multiply the Hadamard code with the input data to get the spread data. Now your transmitted data is your spread data. So for each value of EB by N naught, the you generate the noise, and yeah, you generate the noise. So if it is EB by N naught, that is one way of generating the noise. If it is SNR, that is another way of generating noise. So here selection of variable, that is one is EB by N naught, two is the SNR. So since we have to plot EB by N naught, so it is 1. So we will do this to get the noise corresponding to the particular EB by N naught, where the EB you will get from the transmitted data power. Now that so finally you have to recover this code. So how will you do that? You will basically again multiply the product, but again multiply the uh, signal, the received signal. So the temp signal is your received signal. So you multiply this received signal with the code, Hadamard code. Okay, so the same Hadamard code that you have used here, you will use again here to multiply it again, and then you will get the despreaded sequence. Once you do have despreaded sequence, now it is, since it is a bipolar sequence, you can do a detection, and once detection is done, you count the number of errors that has occurred, and then you plot EB by N naught versus SR, EB by N naught versus BER. So with and without spreading, you see if you do EB by N naught with and without spreading, since you are doing at the bit level, they are mostly same. because you are doing this at the bit level. Okay, bit energy. But if you are doing it at the SNR level, then your BPSK without spreading will have much higher BDR, because at the same SNR, because at the same SNR, when once you're spreading, so basically this same SNR is distributed over a larger bandwidth. This because it is distributed over a larger bandwidth, it gives you a particular, like, what to say, because it is distributed over a larger bandwidth, so it is more spread out, so you will have more decision opportunity. So but if your without spreading, what happens is your SNR is not spread out. Okay, so it is restricted in a particular band, so your BER is much higher. But once you have that lower SNR, once you have that spreaded sequence, what happens is the errors are spread across a large band. So because the errors are getting spread, so sorry, the not the error, the noise is getting spread. So the individual effect of the error is much lower as compared to the without spreading one. So because the noise is getting spreaded, it does not have as much effect compared to as compared to without noise. So as compared to without spreading. So this proves that spread spectrum is more robust to noise. Okay, so this will prove that spread spectrum is more robust to noise. Now with that, I think that will be all for today. So yeah, this was today we did match filter technique acquisition and code acquisition for this code acquisition for frequency hopping. So up to this, is there any doubt? If not, then I will go to some more extra topics on spread spectrum. Slide share. Yeah. Okay, after match filter, there is another thing called serial search acquisition. So serial search acquisition is another method that we will cover here. So a serial search acquisition consists, this is extra from the week's topic. So if you are not interested, can drop out. So serial search acquisition consists of a search, usually in discrete steps among candidate code phases, until it is determined that local sequence is yeah. So here we had done basically correlator output threshold, and we have done serial search acquisition actually already, but we have said we are just doing threshold and we are deciding based on the feedback, but we have not discussed what is the feedback look like. So here okay, so this is the feedback mechanism. So if there is a correlation control, then that is given to a threshold detector. This threshold detector will give a search control. Okay, to give to search control, then it will give to voltage control clock, that spreading sequence generator. So figure 4.3 depicts the principal components of a serial search acquisition. The received direct sequence signal and local spreading sequence are applied to non-coherent correlator that produces the test statistic. Now this test statistic will be passed to the threshold detector. Therefore, if the threshold is not detected, the cell under test is rejected and the phase of the local sequence is retarded or advanced, possibly by generating an extra clock pulse or by blocking one. A new cell is then tested. So basically, if the threshold is not exceeded, then the cell under the test is rejected and the phase of the local sequence. So the local sequence is basically again because it has advanced in the particular threshold detection, it has advanced one phase because 1 unit of time has lapsed. So what it does is it again advances or delays by 1 unit of time and then generates the new PN sequence so that it can be in sync, because even 1 unit delay. So yeah, so it is getting one delay. So even one delay can be fatal for 1 unit of delay can be fatal for PN code acquisition. So it is again set back or advanced by 1 unit phase so that it can be in lockstep. Okay, a new cell is then tested. Then you put a new spreading sequence. Then basically this voltage controlled clock is then manipulated, and then a new spreading sequence generator, a new code is then passed, and that new code is again put through the non-coherent correlator. A statistic is produced. Threshold is detected. If it is yes, then it is given to the demodulator. If it is not, then it is given to the voltage control clock, which adjusts the time, adjusts the time phase again, and then it generates a new spreading sequence which will again be tested, and this loop goes on and on. So yeah, so in search mode, test 1, it will start, test 1 pass, test 2, like that. Once it passes, so this one was a single duel. Now if there are multiple duel, then it will do multiple tests, and when it passes multiple tests only, it will lock. If at any point in any of the duel the test is failed, it will reject. The order in which cells are tested is determined by the general search strategy. Okay. Hmm. The acquisition time is the amount of time required for the acquisition system to locate the correct cell and initiate the code tracking system. So that is the serial search. Okay. Then there are other code synchronization techniques also. So we will be not going into that. This is the acquisition correlator which we have discussed today in a more complex form. And yeah, you can see that this is the EB by N naught and this is the acquisition time. So as the EB by N naught increases, your acquisition time reduces because there is noise related confusion is less. So yeah, if your EB by N naught is low, then yeah, that is there. So noise related confusion is not there, so you can lock on faster and more accurately. So this is the match filter acquisition for frequency hopping spectrum that we have discussed today. And yeah, okay. So that will be all. If you want to see the derivations, they are given in this book. This is called The Principle of Space Spectrum Technology by Don Torrieri. So if you search, you will get the PDF. I cannot share the PDF because it is a, of course, it is an illegal copy, so I cannot search it or share it officially. But if you search by this name, you will get it in the internet. Principles of Spread Spectrum Communication System by Don Torrieri. This is like the fundamental book. Yeah. So that will be all. Thank you. See you in the next week. You may leave. The class is over. हाँ बोल. हाँ हाँ बोल बोल बोल. आ, ना मतलब रखा तो था शायद. ओ ना ना मैं किसी को ही मेल सीसी नहीं रखता हूँ. मैं सीधा आई ट्रिपल मेल से उन दोनों को मिलता हूँ. कोई सीसी नहीं रखता हूँ. कोई रिप्लाई नहीं आया. वाह, दारुण बाबा. So.